Hey everybody, Dr. A here, and in this video we're going to be providing some background information and exploring an example of exercising structural design philosophies. In particular, we're going to be going over the two most commonly used structural design philosophies, which are allowable stress design, abbreviated ASD, and load and resistance factor design, abbreviated LRFD. So let's go ahead and dig into this. So it turns out both of these philosophies, ASD and LRFD, are based on analyzing and designing structures assuming combinations of service loads act on the structure. So this should be a good time to maybe pause the video and write all this down because I've already pre-written some of this information for us. But what do we mean by combinations of service loads acting on the structure? Well, what that means is when we think of a service load, that is an applied force or load of some type. So, for example, service loads are like dead load, live load, snow load, rain load, roof live load, wind load, earthquake load. All of those are collectively examples of service loads. It just means a individual type of load acting on your structure, okay? And so what these two philosophies do is they look at combining the effects of dead and live load, for example, or dead and snow load, for example, or dead and earthquake load, for example. And the way they're combined together is similar but a little different between these two different philosophies, okay? Now, when we get to a full-blown structural design course, like a steel design course or a concrete design course, we spend a lot more time kind of dissecting these two philosophies because they are design philosophies. For the purposes of like a structural analysis course, we are just going to introduce the idea to you and do a couple of small examples, okay? So again, they're both based on taking these different kinds of service loads, dead, live, rain, wind, snow, seismic, etc., and combining them somehow and then placing them on your structure to be analyzed, okay? So where can we find these combinations of these different loads? Well, they're given in Chapter 2 of ASC 7. You can also find them in a lot of other publications like International Building Code, which is abbreviated IBC, or the Steel Construction Manual, or the ACI 318 Concrete Manual. They're summarized in a lot of other places. But, you know, a lot of us have a copy of either International Building Code or ASC 7. If you have ASC 7, it's going to be in Chapter 2, okay? Now, when considering these load combinations, we apply them to a particular effect, okay? We sometimes call these load effects. What do we mean by a load effect? Well, common load effects in a member include things that we've studied in previous courses like Mech of Materials. Common load effects could be reactions, right? Support reactions. It could be internal axial force. It could be internal torque. It could be internal shear force, or it could be internal bending moment, okay? Write all these down. I'm going to say ... So these are all common types of load effects. These are the things that develop either as a reaction or within your structural members due to these applied service loads. So what we do is we say, okay, I'm interested in a particular load effect. Let's say, for example, I'm interested in a reaction, a beam reaction, AY, for example. And I'm going to then apply different combinations of the service loads that are acting on my beam, and then I'm going to combine them together strategically to find what is the worst case AY based on these combinations of loads that, again, are given in Chapter 2 of ASC 7. Okay, so if you have your ASC 7, I'll go ahead and open it up and follow along with me because we're going to start moving into it a little bit, okay? So these are load effects, all right? Reactions, axial force, torque, shear, bending, for example, okay? What about load types, okay? So I already listed those a couple of times. What are load types? These are service load types. This is like dead load, live load, earthquake, wind, rain, snow, ice, etc. ... Okay, so what we do is we look at combinations of these load types and how they develop a particular load effect. Okay, that's the overarching idea behind this. All right, so let's talk about these philosophies a little bit. Let's start with allowable stress design, or ASD. Another term that is used, it's also known as working stress design. It is a classic design philosophy. The way it works is that the elastic stress developed in a member shall not exceed a certain allowable value. Allowable values are determined by dividing the theoretical strength of a member by a factor of safety, which we abbreviate FS. So when we say, when we use a factor of safety, like we've probably done in some other classes before in engineering, we are using a type of allowable stress design. You might be familiar with a factor of safety from a mech of materials class or a fluid mechanics course. This is a type of an implementation of allowable stress design. What about load and resistance factor design, LRFD? Well, this is also known as strength design. It's more modern than ASD. So LRFD is becoming more and more popular in structural design, specifically for steel and concrete. Pretty exclusively, steel and concrete structures are designed based on LRFD nowadays. Basically, the way it works is we increase those service loads, right? Those applied loads like dead, live, wind, seismic, earthquake, etc., by a load factor, and then we simultaneously decrease material strength by a resistance factor. So you take the strength of the material that you're going to use to design and then ultimately build the structure, and you reduce its strength by some resistance factor. So resistance factors are typically less than 1, and then load factors are typically greater than 1. So what you're doing with LRFD is instead of lumping things together in a factor of safety like we do for ASD, what you're doing is you are reducing the strength of the material you're going to use to build your structure, and you're going to increase the applied loads and then combine them strategically. Now, both of these methods have evolved over the years, ASD and LRFD, and there are a lot of modern versions of ASD that is becoming more and more similar to LRFD, but LRFD is really leading the pack right now, and so that's what you're going to end up using a lot more in your later structural design courses. Okay. So let's go ahead and jump into an example while we're on this same video, same topic. And this is a simple example of using load combinations. Now notice I did not write any of the load combinations down in our notes here. And that's because the load combinations, again, they're summarized in other sources like ASC 7. So you really need to be following along with me with ASC 7 preferably, so you can see what these load combinations are. And there are several of them. There are several load combinations for both ASD and LRFD. But you'll find when you tackle a problem like we're about to, some of them you can rule out immediately because they're not going to be applicable to a particular problem. Okay, so let's go ahead and get started. In the given information, we're being asked to determine the governing LRFD load combination and the design compressive vertical reaction at A. So here we have this simply supported beam with a cantilever overhang here. The distance between the roller at A and the pin at B is 12 feet, and then the overhang is 3 feet. You've got a dead load of 300 pounds hanging out at the free end, and then you have a uniform load between A and B of 0.2 KLF. Now notice that uniform load is a live load. It's labeled with the letter L, and ASCE 7 labels live loads with a single capital L, okay? This D right here stands for dead load. And again, if you're looking at ASCE 7 with me, capital D labels that as a dead load, okay? Now, again, ASCE 7 also has several other kinds of loads that they define in Chapter 2. They have a roof live load, S is for snow load, R is for rain load, W is wind, E is earthquake, so on and so forth. But our problem only has dead and live. So I'm going to, under solution here, I'm going to say, note, we only have dead and live loads here. That's the first thing to notice, okay? So now that we notice that, what we can do is start listing out the applicable LRFD load combinations. And again, I'm looking at ASCE 7 right now, specifically section 2.3. So the first load combination for LRFD is 1.4 dead. So what this is saying is when you only have a dead load, you're going to increase it by 40%. That's the 1.4, okay? The next applicable load combination is 1.2 dead plus 1.6 live plus another term, 0.5 roof rain load, or 0.3 times a snow load. I'm sorry, this is roof live load. Did I say? I may have said that wrong. Roof live load is this L sub R. And then we say or, excuse me, 0.5 rain load, capital R. Okay, now none of these are applicable for us because our problem doesn't have any of those. We don't have a roof live load, a snow load, or a rain load. So I'm going to zero that out. So all that we're going to be left with in this combination is 1.2 dead plus 1.6 live. Now, what about load combo 3, 4, 5, so on for LRFD? Well, if you look at the rest of the load combinations in ASCE 7, or maybe you have a textbook open with you too, none of the rest of them are going to be applicable because we only have a dead and a live load. So, for example, if I tried to write down, load combination 3, load combination 3 is going to reduce to 1.2 dead plus live. Okay, notice that middle term 1.6 roof live or 1.0 snow or 1.0 rain. None of that shows up here because we don't have that for this particular problem. We only have dead and live. Well, this load combo 3 is not going to be applicable. Why? Well, because load combo 3 here will always give you a smaller result than load combo 2. Why? Well, it's because in load combo 3 you have 1.0 times the live load, but in load combo 2 you have 1.6 times the live load. So you're ramping up the live load by 60% in load combo 2, and you're not in load combo 3. So load combo 3 will not govern in this. Okay, so really you just have these two load combinations that we have to deal with. So how do we go about solving this? Well, we're interested in the compressive vertical reaction at A. This is the load effect that we were talking about earlier that we care about. So what we need to do is solve for AY, okay? We need to solve for AY for the dead load and then separately for the live load, okay? We're going to solve for AY two different times here. Once when we only have the dead load, and then again when we only have the live load, and then we're going to combine them based on these two load combinations and see what governs, okay? So let's go ahead and do that. I'm going to scroll over, and I'm going to start by saying dead load analysis, okay? So I'm going to say dead load analysis. And then I'm going to draw a free body diagram of that beam with just the dead loads present. So I'm going to call this AY dead. Excuse me, I still got some allergies here. And then I'm going to call this BY dead. And then I've got that dead load of D equals 300 pounds hanging out on that free end. And then, of course, that's a 12-foot length, and that's a 3-foot length. So how do I solve for AY dead? Well, I'm just going to say sum of the moments about point B equals 0, counterclockwise positive. I'm going to say negative AY dead times 12 feet minus 300 pounds times 3 feet equals 0. I'm going to do a little bit of rearranging, and I'm going to get AY dead is equal to negative 75 pounds. What does that negative mean? Well, that means that you've got a reaction of 75 pounds in tension. So in reality, AY dead is doing what? It's reacting downwards, right? So this 300 pounds is trying to yank this point A upwards, and AY dead is holding it down, okay? Now, if you have a negative or downward reaction, we sometimes call that a tensile reaction. We assumed an upward reaction, which means the reaction is compressing on the beam. We did the calculations, it came out negative, so it's pointing in the opposite direction of the assumption, which means it is pointing away from point A, i.e. tension here, okay? So that's part of what I'm going to need to get my answer here in a minute. So separately, I'm going to do a live load analysis, okay? Now, when I do a live load analysis, what am I going to have here? Well, I'm going to have an AY live and a BY live, and I have this uniform load that is a live load in between A and B. And of course, that was equal to 0.2 KLF, or we could say that's 200 PLF, pounds per linear foot, right? And that's, again, a 12-foot distance between A and B. So I'm going to say sum of the moments about B equals 0, counterclockwise positive, negative AY live times 12 feet. And then I'm going to say plus 200 PLF times 12 feet times 6 feet equals 0. And I can do some rearranging. I'm going to get AY live is equal to 1,200 pounds reacting upwards. That's positive. And so that means AY live is 1,200 pounds compressing on the beam, right? So again, I did the calculations, came out positive. So AY is pointing in the direction I assumed, which is up, which is causing a compressive action at that point. And that makes sense. I mean, you've got, 200 PLF pushing down in between A and B, so both A and B should be reacting upwards, i.e. compressing the beam, okay? So now what we're going to do is go into our load combinations, okay? And so that first load combination is, I'm going to say that AYU is going to be equal to 1.4 AYD, okay? Oop. Didn't mean to do that. AYD. Oh, I'm so sorry. So I'll be honest, I just changed apps. My favorite penultimate app quit working. I think they did away with it. So I'm using this new app. I'm just still getting used to it. AY dead. There we go. So thanks for bearing with me. So notice I use some different symbology here. I used U to indicate ultimate, which is just, I'm giving the combination equation, a label here with AYU. So this 1.4 AYD, that's the 1.4 D from earlier. So remember, this was just kind of like this is a generic way of writing it, 1.4 dead. This is more specific to my problem. So when I crank this through, what do I get? Well, I'm going to say equals, and I'm going to get a negative 105 pounds, okay? So that's 105 pounds in tension. So that's not going to govern, and it's really not going to govern because the problem asked for the controlling compressive load combination for AY, okay? So let's go to load combination 2. That AYU is going to be 1.2 AY dead plus 1.6 AY live. So when I punch this through, I get 1.2 times negative 75 pounds, and then plus 1.6 times 1,200 pounds. And when I punch that through, I'll get 1,830 pounds, and that's going to be in compression. So this is my answer. So I'm going to say load combo 2 governs. Okay? Let's see if I can spell that right for us. Okay? And the answer is 1,830 pounds. And that's a compressive reaction force. Now, this is what we would design that reaction or that support for, okay? So again, this is this whole idea of design philosophies and load combinations. Really, we dig into it in a design course like steel design or concrete design in a lot more detail. But for the purposes of like a structural analysis course, we kind of give an introduction to the idea, okay? So that concludes this example and this background information. If you found this helpful, please hit like and subscribe and be on the lookout for other content like this. Thanks for watching.